The electromagnetic spectrum contains many types of waves, one of which is infrared waves. Other electromagnetic waves include gamma rays, X-rays, ultraviolet, visible light, microwaves, and radio. Infrared waves are electromagnetic radiation of a particular wavelength, or color, that we have named infrared. They are between 700 nanometers and 1 millimeter. Note that 1 millimeter is equal to 1 million nanometers. They are just beyond what our eyes can detect on the red side of the rainbow. William Herschel first discovered them around 1800. We are surrounded by infrared every moment of every day. Warm objects, such as the human body, produce large amounts of infrared, and heat-sensitive CCTV cameras work by detecting these infrared waves. Half of the energy produced by the sun is infrared, so we are being bombarded by it constantly. The most common use of infrared in everyday life is remote controls. These work by sending pulses of infrared that spell out a message to an electronic device. This device could be a television, Blu-ray player, or even a computer. Infrared can be used in a similar way for communication. By sending these same pulses through fiber optic cables, transmitting audio to sound systems, or other data through fiber optic high-speed internet services. Thermal imaging cameras use infrared to look at human body heat emissions, both for medical purposes and in night vision cameras. They're often used in the study of animals, as security cameras, or in war. Infrared astronomy has helped us make significant strides in our understanding of the universe. Astronomers can look at an area of the sky that is dark in the visual part of the electromagnetic spectrum, but find the area is extremely active in the infrared. Most objects that have any significant heat produce infrared waves, but not everything is hot enough to light up. There are some limitations with infrared astronomy. Telescopes need to be placed at high altitudes or on hot air balloons because the atmosphere absorbs a lot of infrared before it reaches the Earth's surface. The best way around this is to launch space telescopes, such as the Hubble Space Telescope, which was launched in 1990. Space telescopes have provided us with some wonderfully clear images because there are no atmospheric effects at all. Objects that infrared astronomy has helped us detect include dark and cold dust clouds, protostars that aren't yet producing light, and planets that are hard to see in the visible part of the spectrum due to glare from nearby stars. The light we get from the sun is mostly absorbed by the Earth, but in physics we know that energy is always conserved, meaning it cannot be created or destroyed, it only moves from place to place. So that energy has to go somewhere. After some time stored in the motions of particles in the ground, the energy is re-emitted back into the atmosphere. But although the energy arrived as visible light, the ground re-emits it as infrared waves. This infrared is then trapped by greenhouse gases, like water vapor, in the atmosphere. We call this the greenhouse effect. Meteorology makes use of infrared a lot, not just for climate change research. The energy in the Earth's weather patterns can also be analyzed using infrared images to figure out surface temperatures and cloud types and heights. Infrared waves are just part of the electromagnetic spectrum. To be exact, they're waves that have a wavelength between 700 nanometers and 1 millimeter. This can't quite be detected by human eyes. It's just beyond the red side of the rainbow. Most warm objects produce infrared, and 50% of the energy produced by the sun is in this part of the spectrum. We have many uses for infrared: night vision cameras, remote controls, infrared astronomy, and fiber optic cables. The greenhouse effect is even related to infrared waves because greenhouse gases absorb the infrared emitted by the ground, trapping it on the Earth.